In the first graph, you are seeing a general graph for devices which convert thermal energy into electrical energy. But you know that for the application of solar cell, the device is used only on the fourth quadrant. We are not interested in the plot which lies in the first and third quadrant. When we consider the graph in the fourth quadrant, then for making the analysis easier, we take the mirror image and magnify it, which will become graph like this. However, it is not different, or we can say we have changed the direction of net current. For example, if we take a diode and take a load, we usually take the net current direction like this. But here we are going to take the direction of net current like this. INet will become optical generation rate minus ideal diode current equation. The power delivered to the load by the solar cell is equal to potential multiplied by current, which can be expanded to. Now we have to find the maximum power which can be delivered by the solar cell to the load, and for that we have to differentiate power with respect to potential and equate it to 0. Let the potential and current values at the maximum power V, Vn and Im. This is the final expression for finding the value of corresponding voltage value at which the power delivered is maximum. You can solve this expression by numerical methods like iteration method. Numerical methods are not difficult but are very time consuming. After finding the value of voltage and current which delivers the maximum power, the fill factor can be defined, which is equal to product of current and voltage values at maximum power divided by open circuit voltage multiplied by short circuit current. This is the figure of merit for a solar cell. In the previous lecture, we see some parameters like responsivity, external quantum efficiency, and conversion efficiency. All these were general, but the fill factor is defined only for the solar cell. The expression for maximum conversion efficiency can be defined as current and voltage values at maximum power divided by the incident input optical power. It may be possible that the current values at maximum power is not provided to you, but the open circuit voltage, short circuit current and the fill factor is provided. So, the conversion efficiency can also be written in terms of fill factor like we have simply replaced the value of Im into Vm to be equal to fill factor multiplied by open circuit voltage multiplied by short circuit current.